Okay, so in this lecture, we will discuss on how to select non-nested model. So let's say we have a number of different models. So all models have the same dependent variable, but each model has different set of independent variable. So this is what we call as non-nested model. So the difference between nested and non-nested model as given here. So you consider this what we call as nested model. So consider this model, so model A and model B. Model A, so both have the same dependent variable, but they have different what we call a number of different set of dependent variable. However, model B has the same independent variable that also appears in model A. So model A has four independent variables x1, x2, x3, x4. Model B has x1, x2 only, so without x3 and x4. So we say that model B is nested within model A, so it is a subset of part of model A because it is a special case of model A corresponding to the restriction that beta 3 and beta 4 both equal to 0. So if beta 3, beta 4 both equal to 0, then we have, so we don't have this one up. So meaning that we have the same, the model reduced to be the same to model B. So all the tests considered so far within this course have been found out nested model. So for this model, let's say if you want to choose in between model A and model B, then we can just perform the work test that we discussed before in order to test whether beta 3 and beta 4 are jointly equal to 0 or not. So if we do not reject in our hypothesis, then we meaning that we choose model B lah, because this one x3 and x4 are not do not influence the dependent variable y, because both equal to 0 based on the hypothesis of the web test. So now consider two alternative model, model C and model D. So model C, so we have x1 and x2 in the model. So both have the same dependent variable y, but model D has z1 and z2. So completely different set of independent variable. So in some situation, we need to choose a different set of model, or we need to choose for the model to have a different set of independent variables. So for example, let's say here x1 and z1 are similar variables, so we cannot include both in the same model. So we have to choose either one to be included in the model. Similarly, x2 and z2 as well. So let's say we take an example, let's say y, for example, it is represent sales of vehicle, for example, and then we have x1 and z1 both representing consumer price index. So let's say x1 consumer price index for all items, and then z1 consumer price index for vehicle segment of category only. So this x1 and z1 are similar variables, so that we should not include both in one model or the same model. So we have to choose. So for example, and then this one also the same one, let's say S2 and Z2 also are also similar variables, so we need to choose one of them, we cannot include both. So if we have different set of independent variables, so we call the model as non-nested, okay, non-nested model. So how to choose? So for this given example, where x and z are different variables, we say that model C and D are non-nested because neither is a special case of the other. So in order to decide, so for the case of nested model, we can use word test, but for the case of non-nested model, like we want to choose, for example, here we have two models, so we want to choose one of them. So how? So here we have three different ways that we can use, but each of these approach not necessarily able to suggest or to help us to decide. So we have the discrimination approach, and then later we have the listening approach as well as the last one, what we call as Davidson McKinnon-Gay test. So let us discuss the first approach first, the discrimination approach. So since both models involve the same dependent variable, we can choose between two models based on some goodness of fit criterion, such as R squared or just R squared. Other criteria include case information criteria AIC, SWOT information criteria SIC, model selected that has the highest R square or the R square or the lowest value of AIC or SIC. So meaning that we discriminate models by looking at certain criteria, for example, by looking at R square and star square, and then AIC, SIC, and then we make comparison and see which one has the better value of IC or SIC as well as the R square, against R square. So we need to estimate the model. The model for the given examples, we have model C and model D. So we estimate model C and then model C, model D, and then we compare in terms of R square and so on. So if you estimate the model, you can estimate as usual. So you go to quick. So you have the variable here. So you estimate both models. So model C first. So we have dependent variable Y, and then we have X1 and X2. So this is the model C. So the result of estimation, and then we estimate another model. Model D. So we have Y and then an intercept, and then we have Z1 and Z2. So we need the first one as you can put equation 1, or maybe we can put model C. Model C. And then so this one model C, this one model D. Okay. Okay, so we compare. So in terms of R square, so this model C 0.8 something, but model D, so we have much smaller value of R square and just R square 0.09, and for just R square 0.04. And then for the case of AIC, SIC, and then unclean criterion, so this one smaller than this. So based on the first approach, then it suggests that we should use the model C instead of model D. So if you compare, so just now I explained to you, so we have model C is better in terms of the value of R square. It has higher value, R square against R square. And then we also can look at the sign of estimate. So let's say before we estimate, we expect that we expect all variables to have positive relationship with the dependent variable. So for example, so in this case, X for the model C, both X1 and X2 has positive, but for model D, one of them, Z2, the coefficient has a negative value of estimate. So we also can use that to help us to decide. So in this case, if we expect both variables, the two variables in the model have positive influence on dependent variable, then we choose model C. So lower AIC as SIC as well as unconsistent state, smaller standard error of regression. So this one standard error of regression, this one smaller. Can. And then the second approach, the one that we call as discerning approach. So this one, through this approach, we gather all of the variables in one model, and then we perform the work test in order to decide which one we should use. Suppose we estimate the following nested model. We include all. We combine the variables in both model C and model D. So we have X1, X2, Z1, Z2. And then if model C is the correct model, then we should expect that Z1 and Z2 to have no influence on dependent variable, so that the coefficient for both supposed to be equal to 0. Okay, so jointly equal to 0. So if model D is correct one, then we expect X1 and X2 to have no influence on dependent variable, so that the parameters to the corresponding parameters should be equal to 0. So this testing can be done by the usual F-test that you learned before the work test as well. However, the problem with this testing procedure is that if X and Z are highly correlated, so it is quite likely that one or more of the coefficient are individually statistically insignificant, or although on the basis of the F test they are collectively statistically significant, then there is no way to decide whether model C or D is the correct model. So meaning that if there is high correlation between for just now I provide an example of CPI. So CPI for all items for specific category. So there is a possibility that there is high correlation between the two. So if we include both, there is possibility there's a model for the multi-community problem. Then we have this problem, so meaning that the results of the house testing is not reliable enough for us to make a conclusion. Then the choice of reference this could determine the outcomes of the choice model. So through this approach, we need to estimate a model and include all variables. So this one, we estimate a model and then we include all x1, x2, z1, z2. So the earlier model we name as a model D. Okay, so this one we combine all variables in one model, and then we perform the Watts test in order to decide, which model we should use. So if let's say model C is the correct model, is a better model, or correct model for us to use, then we should expect that the coefficient for this one to be equal to 0 lah. So jointly equal to 0. So we need to test whether the true coefficient for these two equal to 0 or not. So we perform testing as usual. We go to new coefficient diagnostic, walk test. So coefficient number, so number 1, 2, 3, 4, 4 and 5. Coefficient number 4. Coefficient number 5 equal to 0. So the result of the test, the produced p-value, it produced p-value less than 0.05, so we reject. So reject meaning that the Z1 and Z2 have the influence, has a significant influence on the dependent variable. So the result as given here, the one that produces now. So we perform the test, this one, the result. Okay, this is the first one. Okay, and then we perform another one. Okay, this one and the one. So for the first one just now, we test the coefficient for the Z1 and Z2 equal to 0 or not. So since p-value less than 0.05, we reject. So in conclusion, Z1 and Z2 collectively affect the dependent variable Y. And then we also perform another test to test if x1 and x2 collectively influence the dependent variable. So for that test, we need to test this one. Okay, so for the coefficient for x1 and x2, so coefficient number 2 and 3. So you perform a test as usual. What else? Coefficient number 2 equal coefficient number 3 equals 0. So we get this result. So again, the same conclusion, because we reject, so it suggests that both x1 and x2 collectively influence the dependent variable. So basically, we have what we call that we unable, as using this test, unable to decide which model we should use. So for this one, we test for the x1 and x1 and x2. So we reject. So conclusion x1 and x2 collectively affect dependent variable. So we are unable to choose using based on this approach, we unable to suggest us which model, either model C or model D should be used. Now the third one, the Wixon-McLean-J test. So this one, we need to estimate both model C and D, and then produce the fitted values for both model. And then what we need to do, so we use the fitted values to re-estimate the model. So model C, we add the fitted value of model D. So model C, this one model C. So we add the fitted value of model D. Because so this one fitted value of model D, it gives us an idea whether the variables in model D has a significant influence on the dependent variable Y. So if the coefficient, this one, the coefficient after you perform hypothesis testing, it suggests that the parameter of coefficient here is not equal to or equal to zero. So equal to zero, then meaning that the Z1 and Z2 have no influence on the variable. In that case, we choose model C. Okay, so in this case, we estimate for this one, we estimate model D, obtain the residual, obtain the fitted values, and then use the fitted values to the estimate model by adding to model C. So and test the hypothesis that the coefficient equal to zero against alternative not equal to zero using a t-test. So if the hypothesis is not rejected, then model C is preferred to model D, since the variables in model D as represented by the fitted value of model D have no additional explanatory power over the variables in model C. So in order to do that, we need to get fitted value from model D. So now we want to test whether model C is the correct model or not. I mean, the model we should choose or not. So we need to add fitted value from model D to the model of model C. So model C, we need to input fitted value and see whether fitted value has significant, the parameters, the coefficient for that fitted value significantly different from zero or not. Okay. So we need to get the fitted value from model D. So this one, the model D. So we go to view, actual fitted residual table. So we get fitted values here. Just copy and we create a new series. So object, new series, only object, select series, and then we name as fitted. You can use whatever name lah. So, but here to be consistent to the one that given in the node, so we use YD fitted. So YD so we have this. So we paste the value of fitted value just now from model D. Okay, and then we can prepare the same for the another model. So model C, we also have fitted values. You go to view, actual fitted residual table. So you get fitted value. And then you create another series and then you name it as YC fitted. YC. So again, you can use your own or different name. So this one YC. Okay, so now we need to re-estimate model C and then add fitted values from model D. So YD fitted. So we get this, and then you check, you perform hypothesis testing on the parameter for YD fitted value from model D. So in this case, because it produced p-value less than 0.05, so we reject the analysis. The parameter is equal to zero. So the parameter is not equal to zero. So this one. So we wish to test that the coefficient for the fitted value of D, fitted value from model D equal to 0 against after T equal to 0. So just now produce okay, so 0.02 less than 0.05. So we check in conclusion, fitted value of predicted value of the from model D, predicted value from model D affect the value of dependent variable Y. So in this case, we are unable to say that model C is the correct one because the predicted value from model D has significant influence on dependent variable. And then we can do for the model D as well. We can do the same. So model D, we add predicted value from model C. So YC so we do the same. So similarly, we perform hypothesizing on the parameter or coefficient for fitted value from model C, and it is less than 0.05, so we reject. So the same or similar or the same conclusion. This one. So since we reject and then we make conclusion that fitted value from model C infers or affect the dependent variable. So basically again, this one also just like the descending approach. So this one, the post also unable to help us to decide which model we should use. So this basically is summary on how to make how to decide. So there are 4 possible outcomes from this testing procedure. So for this the coefficient for the fitted value from model D, this one from model C. Okay, this one from model D, yeah. So alpha 3 from model C. So basically, if for both tests and setting we do not reject, and then meaning that we accept both model. So again we're not able to select, we are able to choose one, so we got to accept both. But if we reject this one and then we do not reject this one, so we accept model C and reject D, then we can we choose model C. Then if we do not reject this one, the null hypothesis, and we reject the null hypothesis for this one, and then we accept model D and we reject model C, so we choose model D. So if both reject, so we reject both model C and D, so this one we were unable to choose one of them. So if both or neither model is rejected, then no, the answer is possible. So for this given example, we are only able to decide which model we should use based on the first approach, based on discrimination approach. So we suggest, or we choose model C over model D because it has a better value of R square, A star square, as well as AIC, SIC, and Harlan-Quinn criterion.